So we're still in the middle of our Calc 1 review, and the last thing we did was this thing called the antiderivative, right? So somebody remind me what an antiderivative is. What's an antiderivative? You have some function, then you have some other function, and we say this guy is an antiderivative of that guy if what happens? Seth?
F prime is
yeah, so big F prime. So we say this guy is an antiderivative of little f if its derivative is little f, right? Okay, so remember what that is. And then we have this notation, right? So for example, right, x cubed over 3 is an antiderivative of x squared, right? Because the derivative of x cubed over 3 is x squared, right? And you know, as we mentioned last time, if you have one antiderivative, once you find one antiderivative, then you found all the antiderivatives, because all the antiderivatives will differ by a constant, right? Any functions with the same derivative differ by a constant, right? So the point antiderivatives of the same function must differ by a constant, right? And so I'm just going to say this as a fact. It's a consequence of the mean value theorem. Okay, so antiderivatives of the same function will differ by a constant. So we know that all the antiderivatives of x squared will be x cubed over 3 plus some constant, right? So, right, the collection of all antiderivatives of x squared is just everything that looks like this, x cubed over 3 plus some constant, right, for any constant. For any fixed constant, okay? Right, okay. And the way that you write that, the way that one notates that is like this, right? Right, this is basically that statement, right? That the antiderivatives of x squared are these guys. Okay, and this is what we call an indefinite integral. Okay, right. What the language is, you say the indefinite integral of x squared is x cubed over 3 plus c. Right? The indefinite integral of x squared is x cubed over 3 plus c. Right? But that's shorthand. What this thing is shorthand for is saying that it's saying exactly that the collection of all antiderivatives is this. Okay, that's what this is. Okay, so that's the indefinite integral. Indefinite integral. Okay, everybody all right? Anybody have questions? Any other questions? Okay, so definite integral. Something completely different. Okay, what's a definite integral? Can anybody tell me the difference between a definite integral and an indefinite integral? I am
It's in between the 2 points.
So you've got something like this, right?
Yeah.
Right, you talk about the definite integral of a function over an interval, right? So definite integral of function f over an interval AB. Okay. And what does that mean, the definite integral? What does a definite integral mean? An indefinite integral means the collection of antiderivatives. Okay. What do we mean when we say the definite integral? What does this mean? Proceed.
I think sometimes it shows an area.
Shows an area, yeah. So it's it's not exactly an area because you can have negative numbers, right? It's a signed area, right? So, right. So if right, you have some function looks like this, right? And this is A, and this is B, right? And we talk about, so this is the function, the graph of the function f. When we talk about the definite integral, what we mean is that we'll take this positive area and subtract off this negative area and then add on this positive area, right? Right. So it's some sort of signed area of, right? It's some sort of signed area over the interval AB. Okay, right. And how do you calculate? Does anybody remember there's a way? How does one calculate this definite integral? Right. Somebody gives you an arbitrary function and says, well, how do you figure that out? How do you figure out what this area is? Somebody other than Andy. Anybody? Hunter.
You take the integral of the function of an antiderivative, and then you plug in the points A and B, and subtract this way.
Okay. So if you have an antiderivative, if you have an antiderivative, well then you can use it to find the signed area. Okay, you can use it to find the signed area, right? But is that how we create the is that how we start talking about the definite integral? Not really. It's you want to like if you tell a kid, I want to talk about the area here. The way I'm going to define the area is I'm going to take the antiderivative and subtract it at the endpoints, right? That's not like the first thing that you would say to a kid about how you get this area, right? There's something simpler, Mr. Mystery.
Well, what I would do is take a bunch of a rectangle and add them, I suppose.
That's right. So you start by so you do it by so-called Riemann sums. Okay, I hope you've heard this term, Riemann sums, right? You take the base, you take AB, and then you divide it into a certain number of parts, right? And in each interval, in each subinterval, you take a point, you take what's called a sample point. You randomly choose a sample point, right? And then for each of those sample points, you evaluate the function at that height, right? You evaluate the function at that height, and evaluate the function at height. You get these rectangles, right? Evaluate the function at that height, you get these rectangles that give you an approximate area, right? And then what you do is you take finer and finer partitions. So you increase the number of subintervals, right? You increase the number of subintervals, and you do it again, right? You get a different number, and that different number is hopefully a little bit closer to the actual thing than the first one you did. And then you let the number of intervals tend to infinity. So you take the limit as n goes to infinity, and hopefully that gives you, those numbers are going to tend towards something. Okay, so there's this whole procedure you have to go through to calculate the, and I hope you've heard about this before, right? To calculate the, to actually calculate the definite integral, right? You subdivide A intervals, you choose sample points in each interval, right? Then you evaluate the sum of the areas of rectangles. Right. And then you let n go to infinity if a limit exists. If a limit exists, and that's not guaranteed, if a limit exists, we call that thing the definite integral. If the limit exists, we call that thing. If a limit exists, independent of choice of sample points, independent of choice of sample points, then we call that the definite integral. Okay. I'm not going to test you on this. Okay, I'm not going to test you on this. This is just sort of to remind you what a definite integral is. Okay, you see, a definite integral is kind of a tedious thing to calculate. Okay, so this is what a this is one way of defining the definite integral. There's actually a couple of different ways of doing it. You may have seen it a slightly different way. Okay. How you doing? You're looking like.
No.
Yeah. Okay.
I agree.
Okay. Okay. Any questions about this? Again, I'm not going to test you on this. I just want to, make sure that you know the difference between an indefinite integral and a definite integral. Right. Indefinite integral is just collection of antiderivatives. Right. Definite integral is a number. Right. Definite integral is the number. It represents this signed area, the total signed area, and the way you get it is by taking limits of Riemann sums. This thing here, the sum of the areas of the rectangles, is what's called a Riemann sum. Riemann sum. Okay. Okay. Everybody all right? Okay. So now we're going to actually start the material of the course. So that's the end of the review. Now let's talk about let's get into the stuff. Okay. So the thing is that what you see is that calculating integrals is a pain, right? Calculating integrals, well, the way you'd have to do it, if somebody gives you an arbitrary function, right, and says, what's the integral from A to B? Well, if you actually wanted to do it, you have to start approximating, right? And say, okay, I'm going to, take some fine partition of the base, and I'm going to, create all these rectangles, and then multiply, find their areas, and then sum that thing together. And then I have to do it again at a finer scale, and then a finer scale, and a finer scale, until and even that's not enough. You have to let n go to infinity, right? So you have to be able to take the limit in some way. Okay, so calculating the definite integral is a pain. Fortunately, there's a miracle that happens, and that is the fundamental theorem of calculus. Okay, and so here's the statement. If f is a continuous function on AB, And big F is an antiderivative, right? Any antiderivative of little f. Then we can get the definite integral in a very easy way. And that is, you just evaluate the antiderivative at the endpoints and subtract and look at the difference. Okay, so you should think of this as almost a miracle, right? Because it allows you to avoid doing, you don't have to do this Riemann sum stuff, taking limits, whatever. All you have to do is find an antiderivative and then just take the difference of the antiderivative derivative at the endpoints. And that's it. Okay. And notice that your function has to be continuous. Okay, so it doesn't work on everybody. Your function has to be continuous. Okay, so let me give you, and usually this is called fundamental calculus 2. Okay, we'll do one later. So see if you can use it. So here's an exercise for you. I'm asking for the definite integral of e to the negative x over the interval -2, 9. Okay, so your function is e to the negative x, going from -2 to 9. Okay, so take 1 minute and use the fundamental theorem calculus to evaluate it. Turn to somebody nearby and tell them what you got. Okay, so somebody want to tell me how to do it? Somebody want to tell me how to do it? So anybody who wants to tell me? Choose somebody at random. Cannot choose somebody at random. I don't have my gigantic die. What's your name, please? Sorry, I forgot. Yes?
Tanima.
Tanima, you are it. How do you do it? So what's an antiderivative of e to the negative x?
Well, I know that I'm not entirely sure how to do this, but I know that like
Is that right?
if you do like e to anything is it's like e. If you take the derivative of e to anything, it's just e to that thing.
Okay.
And then you do the chain rule.
Right, exactly.
So-
right. So what's the derivative of e to the negative x? Well, you would get, right, so this is e of some function, right? There's a composition going on here, right? So when you differentiate using the chain rule, you get e to that something times -1, right? By the chain rule, right? If you've got a composition, you differentiate the outside guy. Well, that's going to be e to the x, and you evaluate it at f of x, right? And you multiply it by f by f. Right? So this would be e to the negative x times -1. Okay, so this is not an antiderivative of e to the negative x. But you see, if we fix it up a little, we can get an antiderivative just by multiplying it by, if we differentiate negative e to the negative x, well, we do get e to the negative x. Okay, so you see, you can sort of, by trial and error, you can sort of fix it up. Okay, so you say, okay, negative e to the negative x is an antiderivative of e to the negative x. So we found it, right? Right. So this guy is our f, our antiderivative, right? And so we just want to. So what's the answer?
So then you just plug in negative e to the negative 9, and then minus negative e to the to the 2.
Great. Okay. Right. So right. So you get people often write it like this. Sorry. Okay. So you say, well, okay, our f is going to be negative e to the negative x, right? And people often write it like this. They use this notation. They say, they write like this. What they mean by this is negative e to the negative 9 minus negative e to the plus 2. Okay, so you get negative e to the negative 9 plus e squared. Okay, so in case you haven't seen this notation before, right? If you see something like this, you have a function between a and b, what that means is f of b minus f of a. That's just a shorthand for it. Okay. Everybody get that? Okay. Okay. Second exercise, equally same level of difficulty, basically. Okay. So the definite integral of secant squared between pi over 3 and pi over 4. So again, take 30 seconds and write down something. Okay, if there's somebody nearby, talk with them, tell them what you got. Make some friends. Plessy, make friends. Debbie, talk to somebody. Okay, who wants to tell me the answer? What's an antiderivative of secant squared? Tangent, right? So you get the tangent function evaluated between pi over 4 and pi over 3. And then you have to remember what tangent of pi over 4 is. Right? Tangent of pi over 4 minus tangent of pi over 3. Right? Does anybody remember what's tangent of pi over 4? What? Right? Tangent of pi over 3? Square root of 3. Yeah. Okay. If you don't remember those things, that's not so important, right? As long as you could get to here, I'm relatively happy. Okay, that's enough. This part is sort of what you have to figure it out again or remember. In any case, if you got to here, that means you know what you're doing, right? When you're able to find an antiderivative, and you know that you take the difference of the antiderivative at the endpoints. Okay. Okay. Notice that we could have used any other antiderivative, right? Right? All the antiderivatives differ by some constant, right? So if I had said tan x plus 50, right, between pi over 4 and pi over 3, that's also going to give me the right answer, right? Why? because I get tan pi over 4 plus 50 minus the quantity tan pi over 3 plus 50. And the 50s will cancel off, right? I get tan pi over 4 plus 50 minus tan pi over 3 plus 50 quantity. Right? And then the 50s will cancel off and I get the same answer. Right? So it doesn't matter, if you felt like it, you could throw in some constants. But why would you? It's just making extra work. Okay? Okay. Okay. There's another example. There's a cautionary example. -2 to the 2, 1 over x squared dx. Take 1 minute, try it. Turn to somebody nearby, talk with them. And you should be sort of like this. Okay, somebody want to tell me? Somebody want to tell me anything interesting about this? Or how to do it? How not to do it? Bussies? Okay, so your antiderivative, right, is f is x to the -2, right? Then the one antiderivative would be negative x to the -1. I say your negative x to the -1 between -2 and 2. And so you would get -1 over 2 minus -1 over -2, right? And so you end up with -1, right? Is it 0?
No.
It's -1. Nobody is scowling. Nobody's brow is knit. Okay, so there's something wrong with this, right? There's something very wrong with this, right? 1 over x squared, is that a positive function? Is that positive? Yes, it's always positive, right? And yet we integrated it over an interval and we got a negative number. Okay. Right? The fundamental theorem of calculus doesn't seem to be working. Yes?
Is it because it's not continuous?
It's because it's not continuous. Okay. So you can't use the moral. The moral is fundamental theorem of calculus. You can't just use it blindly, right? Right. You have to satisfy the conditions of the conditions of the theorem. You have to have a continuous function, right? Continuous function on that interval, antiderivative of the plot. So don't. You have to know what you're doing. Continuity was crucial. Now, why was continuity crucial? You don't know yet, okay? Because we haven't talked about the fundamental theorem of calculus, why it's true. Okay. But we'll tell you in a minute. Okay. So watch out. Fundamental theorem of calculus doesn't apply to discontinuous functions. you wanted the area of this thing, well, you'd have to do it in some other way. Okay. Fundamental theorem of calculus 2, we're not going to explain yet. Instead, we're going to talk about the fundamental theorem of calculus, number 1. Okay. And we'll get fundamental theorem of calculus 2 from fundamental theorem of calculus 1. Okay. That's why we're not going to explain it yet. We'll explain this one, and then we'll get the next one. Okay. Okay. So this one, so where the other one was about evaluating definite integrals, this one is about creating antiderivatives. Okay, so first this guy's about creating antiderivatives, the other guy is about evaluating definite integrals. So it says the following. If you have, so let f be a continuous function on AB, then create a new function. Okay, this new function is going to be funny. We're going to call it big F because we're going to see that this guy's an antiderivative. Okay. We don't know that this guy's an antiderivative yet, but we're going to see that it's an antiderivative. So we create this new guy. We'll call this guy the area function. Okay. And the way we define him is by integrating the little guy from a to x. Okay, so over here I'm going to draw a picture. Right, you've got some continuous function. You've got some continuous function little f. Okay, and then you define this new guy big F. Okay, and the new guy we're going to say, wait. So if I want little f of x, what's little f of x? On this picture, if this is x, what's little f of x? Where is it? Well, it's just this height here, right? It's just this value, right? So this thing here is little f of x. Okay. Big F of x is going to be, what's that on this picture? Well, it's the integral from a to x of little f. Okay, so that would be the signed area from here to here. Okay, this whole signed area is big F of x. Okay, it's all these things together. Okay, that's the guy. What you see, I'm calling it the area guy, right? It's the signed area from a to x. And for example, if I talk about f of b, big F of b, well, that would be the whole signed area from a to b. Right? That would be just the definite integral of little f from a to b. Is everybody okay? Anybody confused? Talk with each other for like 20 seconds to see if you have any question. Turn to somebody nearby and say, I get it, or I don't get it, or whatever. Okay, anybody have a question? Does everybody see what big F is? Big F is this. Big F of x is the integral from a to x. Right? The integral of little f from a to x. Okay, so here's back to the theorem. You have a continuous function. You create this new area function guy. Then big F is differentiable, and its derivative is little f. The derivative of this area guy is actually the original function you started off with. Right? In other words, big F, the area guy, is an antiderivative of little f. So what this is saying is that you can create an antiderivative for any continuous function, right? Any continuous function, you can make an antiderivative out of it. Now you might be thinking, like, why do we want to create antiderivatives? Seems like an odd thing to do, right? But we'll need this to get the second fundamental theorem of calculus. So that's, for us, that's its main purpose. Okay, so let's try to think of why is that true. Why is that true? Why is it true that the derivative of this guy, right, is going to be that guy? We've got this area function. Why is it true that the derivative of the area function is going to be our original function? So let's think. Right. F prime at x. What's f prime at x? So we're just going to go back to what these things are. What's the derivative? What's the derivative of a function? What's the derivative of a function? You know, we said last class, it's the limit of f of x plus h minus f of x over h as h goes to 6. Right? That's what a derivative is. Okay. At the end of this, we'll see, miraculously, we'll see a little f appear. Okay, but so far so good, right? This is just the definition of derivative, right? Okay, so now let's think of what that means for our guy here, right? Capital F of x plus h, what is that? What's big F of x plus h? Well, big F of x is the integral from a to x, right? So big F of x plus h is going to be the integral from a to x plus h of little f. When we subtract off the integral from a to x of little f, right? And we divide the whole thing by h. Right? Everybody okay? We haven't done anything. We just used, this is what we said big F was. Okay. Okay, now let's think. The integral of little f from a to x plus h minus the integral of little f from a to x. Can anybody express that more simply? The integral from a to x plus h minus the integral from a to x. Don't blurt it up, don't blurt it up. Anybody see it other than Franco? Okay, Miss with the hat.
The integral from x to h.
The integral from x to h here, almost. So we're going the integral from a to x plus h, and then minus the integral from a to x. So we get this area minus this area, right? So not from x to h. The thing is that h is some small number over here. H is over here actually, right? This is x plus h, right? So the integral from x to to x plus h. Yes, the integral from x to x plus h. So everybody see that? Right? We take the integral from here to here, right? This area, and then we subtract off this area, right? And what we're left off with is this thing here, right? Right? This minus this is going to be this thing here, right? So I'm going to erase this picture. Sorry. Space. So we get the limit as h goes to 0 of 1 over h times the integral of x to x plus h over f. Of f. Right? So x plus h. Right? So you end up with this thing here. Okay. Now let's think of what this thing is. If we take this area, right? This thing here is the area, right? This thing here is the area, and we divide by h. Okay. Here's the best part. Okay. Here's the best part. You divide by h. Right? What do you get when you take this area and you divide by h? You take an area, you divide by a length. Take an area, you divide by a length. What do you get? The height, say.
Yeah.
You get the height of a box. You get the height of a box with the same area, right? So take the whole area, divide by this. This thing here is the height of a rectangle with the same area. Right? Does that make sense? Okay. In other words, what you've done is you've let the water, if this is water, you let the water settle, right? And you get the height there. In other words, what this is an average height. This is actually the average value of f on x plus h. Okay, wait. You let it settle, so you get like the mid height, basically, the average height. The mean value. Okay. So now, so here's the picture. Here was x. Here's x plus h. Right. Now we let h go to 0. We let h shrink to 0. What do we get then? We're going to get the average value of f over this interval, and we let the interval shrink to 0, shrink in length to 0, right? What's going to happen to the average value, right? I go over here, I'm looking over this interval, I'm looking over this interval, I'm looking over this interval, I'm looking over a very tiny interval, right? What happens to the average value of f over this tiny interval? Do you see what happens to it? Here's my function, here is x, here's x plus h. I say, I get the average value over this interval. That's something like this, right? But then I let my interval become tiny, right? What's the average value over this interval? What can you say about it? It starts getting closer and closer to f of x. Here's f of x. My interval is tiny, so my function doesn't vary that much anymore. Right? As I get closer and closer, this thing turns into f of x. And so that's why this is how you understand the fundamental thing of calculus. That if you create this area guy, then its derivative is just the original function. its derivative is just the original function. Okay, let's stop here for today. Anybody have? Let's stop here for today. If people have questions, come up and ask. Anybody have questions? So just think, what part of this, if it's confusing, what part of it's confusing, right? This part I think should be all right. We're just saying, when you take a derivative, this is what a derivative is. Second part, it's just, what is big F? That the only thing we used was, what was big F? Well, big F was the area function. Third part, with that difference of areas. Difference of areas is going to be this last bit of area. Right? So that's not hard. Maybe the last part is the hard one. Right? The last part is the hard one. You think, well, what does this mean? This thing is the average value over this interval, and then you let that interval become really small. Well, what happens to the average values? Well, right? If I look over this interval, the average value is pretty close to the value at this left endpoint. So that's the thing that you want to get if you haven't. Okay, that's it for today.